Let us consider a potential with delta functions. So potential with delta functions. So this will be a one-dimensional potential v of x of the following form. We have minus v naught times a times a sum of delta functions, and I will write them as follows. Delta of x plus 2a plus delta of x plus a plus delta of x plus delta of x minus a plus delta of x minus 2a. So it's 5 delta functions in total. And you can see that these delta functions are located at different positions on the x-axis. So if we wanted to plot this potential, here is the x-axis, here is the potential, x equals 0 is here, x equals a is here, x equals to 2a, x equals to minus a, and x equals to minus 2a. Well, this x plus 2a delta function fires when the argument is 0. So that's the delta function that is located at x equals to minus 2a. And with v naught positive and a positive, so we'll write here v naught positive and a positive. This delta function is here. We'll draw it like a little arrow pointing down. This delta function, of course, is infinitely deep and infinitely narrow, but we'll just draw it like that. There's another delta function at minus a. There's a delta function at x equals 0, delta function at a, and at 2a. So this is the potential. There's only delta functions in here. That is, the potential is 0 everywhere except at those points where we have the delta functions. And in terms of making sense of the potential and the units, the delta function has units of 1 over length. Therefore, for the potential to have units of energy, we've put here the a, which has units of length. So a times the delta function has no units, and the v naught has units of energy. So v naught has units of energy. It's not the depth of the delta function, which is infinite, but it gives you a feeling of how strong the delta function is. So what we want to understand, these are attractive delta functions, is what kind of bound states we have here. So this is we've plotted here the potential v of x. Here is the x-axis. So what kind of bound states do we have? So the first thing we need to understand is what is the effect of a delta function on a wave function. So let's consider a simpler problem here to the right. So what is the effect? The effect of a delta function on the wave function. That's our question. So for that, a single delta function is enough. Let's assume you have the x-axis, and there's a delta function at x0, some kind of negative delta function, so that the potential, as far as we are interested, is lambda times delta of x minus x0. So lambda is the strength of the delta function. It's equivalent of v naught a or minus v naught a, but now I want to leave it just like a lambda that you can remember and you can use for any analysis. So we need to understand what does it do, the delta function, to the wave function. So for that, you certainly have to go and look back at the Schrödinger equation. So what is the Schrödinger equation? Minus h squared over 2m, second derivative dx squared of psi, plus v times psi. So we're interested in the potential is 0 except at this point. So in this area, in this region, we can just put lambda delta of x minus x0, the potential, times the wave function. And that should be equal to E times the wave function. And for the problem we're considering here, of course, we expect the energy to be negative, to have a bound state, but here we have our equation corresponding to this problem, just a single delta function. And we want to understand what does the delta function do or tell us about the wave function. As you will see, it tells you something about the discontinuity of the slope of the wave function. That's what we want to show, that the delta function just affects the way in which the slope of the wave function is before the point where the delta function appears and after. So for that, we'll take this equation and we'll integrate it from x0 minus epsilon to x0 plus epsilon, 2 points here. So let's see what we get. We have minus h squared over 2m integral dx from x0 minus epsilon to x0 plus epsilon of this thing, which is ddx of psi. There are two derivatives of psi, so I'll put ddx of psi prime meaning ddx of psi, plus lambda integral from x0 minus epsilon to x0 plus epsilon of delta dx delta x minus x0 psi of x is equal to the integral again from x0 minus epsilon to x0 plus epsilon dx e, that can go out, but I didn't, but it will go out very soon. So from the original Schrödinger equation, we've now integrated it, and if the Schrödinger equation holds, the integral version of it, in which you integrate from a little before the singularity and a little after the singularity, should still be an equality. So what do we do next? Well, we can evaluate some of this. Let's look at the first term. This is the integral of a derivative. So that's the function evaluated at the top value minus the evaluation of the function at the lower value. So we have minus h squared over 2m psi prime evaluated at x0 plus epsilon minus psi prime evaluated at x0 minus epsilon. Good. Next term, lambda is there. There's a delta function. Well, delta function integrals are easy. They just fire at the point where the delta argument of the delta function is 0. So this will give us just psi at x0 because, happily, the point where it fires is within the interval of integration. So we get here plus lambda times psi of x0. And on the right-hand side, well, let's assume epsilon is small enough that we can evaluate this integral. So we will have e, and the integral from a little before x0 to a little after of psi of x. Now recall, the Schrödinger equation forces psi to be continuous. So in this small interval, psi cannot change much. So a good way to estimate this integral, and the leading contribution, is just the range that you're integrating times the average value of the function there. And since epsilon is small, this is accurate. Whenever you write epsilon, you think it's small, but so this is roughly equal to 2 epsilon, because that's the range, times psi at x naught. And there would be here corrections of order epsilon squared, but we won't worry about them. Now what do? We just have to restate this in clear language. We want to let epsilon goes to 0. So in that case, this term will go to 0. And therefore, these two terms on the left-hand side must add up to 0. So what are they? They are minus h squared over 2m. And I'll put some notation here. I will call this difference the delta of psi prime at x0. So that's the discontinuity of psi prime at x0. You see, psi is continuous, but psi prime, the slope, cannot be continuous once you have a delta function. In fact, that's what we're going to show right now. It's going to come out. But here you have the change of the slope at x0. So if you want, this is defined to be psi prime at x0 plus epsilon minus psi prime at x0 minus epsilon, the limit as epsilon goes to 0. So that's the definition. And then what else do we have? Well, we have plus lambda psi at x0 equals 0. The right-hand side goes to 0. So from this equation, we have a simple result. We can solve for this discontinuity in the slope. And what do we get? Delta psi prime at x0 is equal to 2m over h squared lambda psi at x0. This is a very nice formula, so I'm going to box it with color, make it look nice. Key identity for potentials with delta function. It's telling you that the delta function causes a discontinuity in the slope of the wave function equal to a quantity which is the product of the strength of the delta function times the value of the wave function at that place where the delta function sits. So it's not a constant change of slope. It depends on the value of the wave function. So the main takeaway from this is that delta psi prime is proportional to psi at the singularity. That's what this says. And the constant of proportionality is the strength of the wave function, of the potential, of the delta function, times this universal 2m over h squared constant. And the sign is correct. We derived it properly. This came to the other side with a minus. They canceled. And this gives you a little bit of intuition as to what's going on. So now that we have this result, you can also see that if psi of x0 is equal to 0 for some accident, the delta function has no effect whatsoever, because the wave function, the slope, is continuous. This right-hand side is 0, and the wave function doesn't see anything. It doesn't see the delta function, and it's not affected at all. So in this case, delta psi prime is equal to 0. The wave function and the derivative of the wave function are continuous. So well, let's get a little more intuition about the sign. So I'm going to move to another page. And let's consider it here. Let me write this key equation again. Delta psi prime at x0 is equal to 2m over h squared lambda psi of x0. So a bit of intuition here about the signs of this equation. Suppose you have an attractive potential. So here is the potential v of x, and you have a delta function that points down. So lambda in this case is negative. So suppose you have a wave function that looks like this. Is this consistent? A wave function that has a slope discontinuity of this form at the place where the wave function happens. So let's see if the signs work out right. Well, we have the wave function that is positive at this point, and lambda that is negative because it's an attractive delta function. So the right-hand side is negative. So it means that the slope a little after the singularity minus the slope a little before the singularity should be negative. Indeed, the slope after the singularity here is negative. To the right of x equals 0, say, it's negative. And here to the left of x equals 0 is positive. So negative minus a positive is more negative, and indeed, this is the kind of discontinuity you would expect for an attractive delta function. So, let's go back to the problem we were trying to discuss, a potential with many delta functions. And now that we've dealt with the effect of the delta function of the wave functions, which is just a boundary condition for the derivative of the wave function, we need to consider what the wave function is doing in the space between the delta functions. And in that space, we said that there's no potential whatsoever. So the Schrödinger equation becomes simply psi double prime is equal to minus 2m e over h squared psi. So the second derivative, we took the 2m over h squared to the other side. There's no potential, and you have psi again. So this is a rather simple equation. Remember, E is negative for the bound states we're looking for. So I will write this as kappa squared times psi, because this whole number here is negative, is positive. There's a minus sign, and E is negative, so the product is positive, and that's kappa squared. So here, kappa squared is defined to be minus 2m e over h squared. Now, that's fine. Now we have a general solution of this equation. Psi squared equal kappa squared psi. It's solved by psi of x equal to a e to the minus kappa x plus b e to the plus kappa x, where a and b are two constants. This is the general solution for the wave function in between the delta functions, where the potential is 0, and given that we have a bound state that we're trying to look for that has, therefore, as any bound state, negative energy. So let's try to understand this type of function. If you have a psi that has a decaying exponential and a growing exponential, is a fact that this wave function can only be 0 at one point. It either is, suppose one of the factors is there, like this factor, well, it vanishes then at x very, very large. This factor vanishes at x very, very small. But when both are present, you have the situation where the wave function can only vanish at a single point in between. And this is not too difficult to understand. Suppose I have a term. Here I'm going to plot something. Here is x. And I'll have a term with a growing exponential. I'll call it b tilde e to the kappa x. It grows forever. B tilde is positive, and in fact, it's the value here, because when x is equal to 0, this is 1, and this function becomes b tilde. And now consider the other function like this, a tilde e to the minus kappa x. It decays because as x grows, this exponential becomes smaller and smaller. And at the same time, you have here a tilde. So these are the sort of two ingredients here. The signs may be different. I put an a tilde here and a b tilde so that you don't think these are necessarily the same. But if you think of these two functions, if both were positive, the sum is never 0. So this is like the cosh function that has no 0. But if the signs of these two were negative, they would cancel, well, if one was positive and one was negative, they would cancel at the place where they're equal, and therefore you produce 1, 0. But if you produce 1, 0, there's no other intersection. So you can only produce 1, 0 here with these two wave functions. So this wave function over here can only have one zero, kind of, in a region of parameter space. You don't find more than one zero. So we can go back to our problem. And what was our problem? We had 5 delta functions. 1, 2, 3, 4, and 5 at 0, a, 2a, minus a, and minus 2a. And I want to make just some comments about this. For example, whatever bound state that you have, try to think what's happening beyond x equals to 2a. I claim that there's no zero for x greater than 2a. You see, beyond, what I mean by that is that the wave function doesn't cross the axis at any point beyond x equals to 2a. Now look, what is the only solution you can have on this part of the real line? The only thing you can have is a decaying exponential. A growing exponential would not be normalizable. So here you must have some sort of c e to the minus kappa x, where c is a constant. That's the only thing the solution can be. If that is the solution, the 0 is asymptotically reached, but there's no 0 in the sense of cutting the axis. Now, another possibility is that the constant c is 0, the wave function is 0 everywhere here, but that's actually quite catastrophic. If the wave function is 0 all over here, it would be continuous around this point, and moreover, since it's 0, the first derivative is going to be 0 as well. The discontinuity is going to be 0 because the wave function vanishes at that point. Therefore, not only is the wave function and its derivative 0 a little to the right of 2a, but the wave function and its derivative would be 0 a little to the left. And therefore, by the general property of the Schrödinger equation, if the wave function, its derivative is 0, it becomes 0. So it will be 0 all the way here, and then by the same argument everywhere. So c equals 0 is no good. So indeed, you cannot have a 0 for x greater than 2a. On the other hand, you can have zeros in between the delta functions. In between any pair of delta functions, the wave function can be 0, because in between any two delta functions, the general wave function is of this form, and that, for suitable coefficients, can give you a 0. So the wave function can cross the axis in between any of these points. So that's a possibility. It doesn't have to happen, but it's a possibility. So, for example, you can now think about what's going on. You can have one 0 at most between any two delta functions. And if you look at this potential, then again, here is the delta functions. 2, 3, 4, and 5. You could have a wave function that is like this, that doesn't have any 0. Something like that would have discontinuities of the right type, as we discussed at those points. This is somehow the way the ground state wave function looks. If you have one 0, remember a potential, so this is no zeros of psi, so this is the ground state, roughly. If you have one 0, since the wave function has to be either symmetric or anti-symmetric, this potential has parity symmetry. It's invariant under letting x goes to minus x. So the wave functions are, by uniqueness of a one-dimensional potential, either symmetric or anti-symmetric. So the first excited state, you would expect it to have one 0, and if it would be symmetric and the 0 would be at this point, then you would have to have another 0 here, so you have 2. The only way to get a single 0 is to have it at the origin, and that's what you would expect. So the first excited state would have one 0 at x equals 0. So this is the first excited state. Then you could have two zeros, and those could happen any place that are symmetric. Then you could have three zeros. It would be another antisymmetric, 1 0 here and 2 zeros somewhere in a symmetric way. And you could have 4 zeros, and you have here, so 2 zeros, 3 zeros is also a possibility, and even 4 zeros is a possibility. You would have a 0. You cannot have it beyond the last delta function, so it would have to be here, 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 and here. There we go. These are the possible zeros of the potential, and therefore you have from no zeros to 4 zeros, so there's a maximum of 5 bound states. Now, they may all not occur. If the delta functions are not strong enough, you may have one. You will always have one, at least. You may have 2, 3, 4 as you make it stronger. At some point, when the delta functions are sufficiently strong, you will get all those states. So this should give you an idea of how to solve a similar problem in the homework, dealing with delta functions. If you haven't seen much of this before, you definitely should first solve the problem of one single delta function and finding the bound state energy of it. It will be very simple. We've done most of what you need, and you should be able to find that with a little bit of work. So good luck with that, and take care.